All right, boys and girls, this is the rock cycle. Get it? All right, the rock cycle in Michigan. This PowerPoint was done. What's causing that? Oh, that thing. Okay. This PowerPoint was done by the Michigan Department of Environmental Quality. But if you remember, I told you they no longer exist. The organization now is called EGLE, Environmental Great Lakes and Energy. So MDEQ helps take care of our lakes. All right. They did this PowerPoint. I changed it up a bit, so some of the stuff is mine, some is theirs, but it's mainly theirs. The rock cycle in Michigan. You don't write most of what's in here. You'll know because it's yellow, and I'll tell you when to write down. Okay, so just pay attention. First of all, what is the rock cycle? It explains how rocks and natural processes are related. You need to fill in the words on your chart, please. Can you do color? Just with pencil. I'm going to pause while you guys do this. Okay, so we've been working on the rock cycle along. So this is another way of just showing the rock cycle. There are three types of rocks, as you know. Igneous rocks are formed by heat, by magma and lava underground. Igneous rocks can become metamorphic rocks. They can also become sedimentary rocks. They can also become igneous rocks again. We're going to learn how this chart works later. It's a really nice representation of the rock cycle, how things are moving in all directions. The more traditional definition of the rock cycle is this, and you need to write this word for word on your paper. A sequence of events involving the formation, alteration, destruction, and reformation of rocks as a result of natural processes. That goes on your paper, please. All right, so let's look at this a little more closely. It's a sequence of events. The formation of, what's formation means? It means to form, right. To alter. Alteration means to change. Good. Destruction means to destroy. And reformation means to reform. So we're just changing things up and constantly moving from one thing to another over and over again. That is the actual definition. You're going to have to write this on your take-home test this week. Make sure that your notes are very careful and very clear, because 1/4 of your test involves these PowerPoint notes. So make sure you're careful about that. So we're going to use that graphic that you can see back here to represent the rock cycle. We'll be seeing it again and again. But before we look at the full rock cycle, we need some background information. And first of all, you have to know that there are three main classes of rocks. All three rock types are found in Michigan. And those three types are cemetery, metabolic, and ingenious. Right?
No.
Are those the three rock types? No, the three rock types are sedimentary, metamorphic, and igneous. You guys are not writing unless I tell you to, so be careful. Be careful. Okay? Okay, some of the kids here were confused. These are not the answers to the bottom of your first page. We're on this sheet right here. It's maybe this way. You can't really see it, can you? But those are not those answers. All right, moving on. So here we have James Hutton. So he lived in the 18th century. He was a pretty bright man. He was a lawyer, a doctor, he was a farmer, and he was the father of geology. He's the father of modern geology. He's the one that came up with the rock cycle. He went to visit a place in Scotland, and he saw that there were cliffs and mountains, and he went, whoa, because in his day, people thought the world was just like it is how they saw it. In other words, if you saw a mountain, that mountain was always there. If you saw river valleys, they were always there. They didn't understand that we have something called plate tectonics today. They thought that the way the world looked is the way it always was. We now know that that is not correct, but that's the world view. Until James Hutton said, whoa, wait a minute. I don't think that's the case. I think there's a lot going on here. And I think those rocks were formed in a specific way, and they've changed over time. So two things he knew about. He knew about solar energy and gravity at the surface. What he did not know was about radioactive heating from inside the Earth. So there are three forces that drive the rock cycle. And those sources are, you can write these down at the bottom of the first page, solar energy, gravity, and radioactive heating. Those are the major forces that drive the rock cycle. All right, so we've already talked about solar energy and gravity. We have not talked much about radioactive heating. When we get to plate tectonics, we'll talk about that a lot more. In the meantime, we do know that the rock cycle, because of these things, will self-sustain itself for thousands of millions of years, billions of years. It will just keep going on and on and on and on. In fact, this is rock cycle. We call that an old-fashioned theory. But do you think it holds up with today's scientific thinking?
Yeah.
Sure does. Remember, science is about disproving. If you can disprove it, the theory goes out the window and you start over again. But the rock cycle has not been disproven. The rock cycle theory is still out there. And even in today's thoughts about plate tectonics, it's still very important, which we'll get to later this year. This is a picture of plate tectonics. These plates are moving. We're not going to talk more about that right now, but you will see this map a lot in the future. All right, so you can think of, and I'll tell you when to write, the mantle, crust, and surface of the earth can be thought of as a giant recycling machine. Rocks are neither created nor destroyed, but they are redistributed and transformed from one rock type to another. I'm going to pause while you fill in the yellow at the top of page 2. So looking at this a little more closely, the earth is kind of like a giant recycling machine. Only God can create something out of nothing, correct? Yeah. So rocks are not created from nothing. They come from other things. And you can't completely destroy a rock and turn it into oblivion, like completely make it go away. It just changes. Destroy is not the same thing as changing, all right? But you can redistribute them. You can move them around. You can transform them. That's what this is. So here we have igneous rocks down here being formed in the mantle. Some come up through lava. We have igneous rocks coming extrusive and intrusive. We have metamorphic rocks changing, heating, and pressurizing. And we have sedimentary rocks, of course, on the surface when you have your weathering and your transportation, your deposition, and they layer and compact over time, right? So those are the 3 rock types. Giant recycling machine. That's pretty much what the earth is when it comes to rocks. If you were to ask a geologist what the earth is, what do you think he would say? Any ideas?
I think he would say the earth is one big rock.
Exactly. That's it. Earth is a big giant rock. That's what he'd say. Earth is big rock, and then there's a bunch of stuff going on in the surface and the crust, and yeah. Okay. Now, do not write till I tell you. Here we have a diagram of the earth. You have a bunch of little slots. In those slots, you're going to fill out the names of these layers. Under the slots, you're going to write the temperatures. You do not have to write the depths, okay? So in the slots, write the labels. Under the slots, write the temperatures. I'm going to pause the video. Okay, so this is called a temperature gradient because the deeper you go inside the earth, the wetter it gets. Everybody? The hotter it gets. Very good. So we have the core, which is the coolest, all the way down the inner core, which is 4,300 degrees centigrade. So it gets deeper. We'll get more into this when we get plate tectonics. I just want to do an overview right now. However, this diagram is going to be on your test. I want you to color it for me. I want you to color, here's my black marker. I want these 2 layers right here, green. This is your crust. Whoops. Nope, nope. This right here, this outer layer is your crust. See if I have the right colors on this. Yeah. This whole area as well is going to be crust, okay? Then these 2 layers right here are going to be your mantle, your inner mantle, an upper mantle, lower mantle. So these are mantle. And then these right here are your core. So I would like the crust colored green. I would like the mantle colored blue. Yes, I want to make sure I get the same one as on your test. And nope, red. Mantle red. And the core will be blue. Okay, so I'm going to pause while you do that.
Wait, so
Should have the core. For you guys at home, if you don't color this whole bit, I won't take it off. I won't take points off. But you do have to have this part colored green, that skinny line, and these 2 layers red and those 2 layers blue. So make sure that you get that properly done. All right, here we go to continue on. So, I should probably erase that, huh? Get that out of there. Messed that up. So now we've got to understand the largest components of geology will be the crust, mantle, and core. We're going to go down to the smallest components. So this is the hierarchy of elements of geology. You're going to see this twice in the PowerPoint. The bottom of the sheet, you'll be filling in the yellow. Atoms make up elements. Please write it. Elements combine to form compounds. Like an element would be oxygen. If you add it to hydrogen, you have H2O. That's a compound, right? These natural compounds and elements combine to form minerals. And these are some of the crystal forms of the mineral forms. Remember, all minerals have a crystal shape. Those are some of them. Minerals make up rocks. So if I ask you what a rock is, you say a rock is made of mineral. Minerals make up rocks. And finally, rocks make up the earth. So we have something called atomic theory, and it says that all matter is composed of atoms of about 100 chemical elements. There are actually a few more, but there are about 100. It also says that compounds are formed when you combine these elements. This is basic chemistry. These elements can be based on something called the periodic table. Have you seen this before?
Yes.
Good, good. I know that you've learned this before in 5th grade. The periodic table has the elements. It has their atomic weights, their atomic numbers. It is a marvel of organization. And when you're older, you'll understand why it's set up this way. It's just brilliant. Just brilliant. But for our purposes, only 8 elements make over 98% of Earth's crust. Over 8 elements make over 98% of Earth's crust. Can you see that at the top of page 3? Yes. Circle that. That's important. You need to know that. Circle it. Only 8 elements make over 98% of Earth's crust. I've got those 8 elements showing here, and I'm going to give you the chemical symbols for them. So write them as they come up. So oxygen, the chemical symbol is capital O.
So where do we write that?
Right by
Look at the top of page 3, and you'll see the chemicals listed there. Okay, the elements. The next element is silicon, capital S, small I. Remember we made the silicate tetrahedrons? Remember?
Yeah.
The next one is aluminum, capital A, small L. This will be on your take-home test. The next one is iron, capital E, F, small e. This comes from the Latin or Greek, I can't remember which, ferrous, capital F, E, iron. The next one is calcium, capital C, small a. Think calcite, right? Calcium carbonate. The next one is sodium, capital N, small a. If you're wondering where the Na comes from, way back when the Egyptians would bury their dead, they would encase them in something called natrium. And natrium is simply salt. And the formula for salt is NaCl, sodium chloride. So it comes from natrium or salt. K stands for potassium, capital K, potassium. I do not know where the K comes from. And Mg stands for magnesium, capital M, small g.
Wait, what was
Okay, moving on. We're going to see this again. You've seen this already. You don't have to write it again. Basically, again, atoms make up elements. Elements make compounds. Compounds and elements make minerals. Minerals make rocks. And rocks make up the earth. So what are minerals now? We've already had our lectures on minerals. We're going to back up a little bit. Let's see what this PowerPoint says about what they are. So the characteristics of minerals are, you do not have to write these down. They are naturally occurring. They're inorganic elements or compounds. They have an orderly internal structure. They have a characteristic chemical composition. They have crystal form. and they have the physical properties of a solid. Naturally occurring, crystalline, solid. So my definition is, and you write it there please, minerals, as you know, are naturally occurring crystalline solids. You're writing this in the 4 boxes where it says definition of a mineral. All right, there are over 300 minerals in Michigan. There they are. There they are. Stand up when you think you see one that you recognize, please.
I can't even see a word.
Sure. I see calcite there.
Yeah. I see
Amethyst, yeah. Zircon.
I see
Yeah, if you're looking up, you'll see them. Okay, have a seat. And each mineral, each one of these has its own identifiable properties or characteristics. And we did some mineral tests and stuff like that. So, your sheet, under those 4 boxes, write in, please, minerals combine to form rocks. Under the 4 boxes, you have this, minerals combine to form rocks. Now, some rocks are made up of just one mineral, like rock salt, and you can find it under the city of Detroit. You used to be able to go down into the salt mines down there. You can't now unless you have special permission, but Detroit is sitting on a huge salt mine. Other rocks are made up of many minerals, like granite. Granite has what 3 minerals in it? Who can remember? What's one?
Feldspar.
Feldspar and?
Mica?
And?
Quartz.
Quartz. Very good. Okay, now we have some of the basics. We're going to talk more about the rock cycle itself. Back to this. On your sheet, there's like a little wavy box. You put the yellow part in here. Rocks are weathered, eroded, transported, deposited, and lithified to form sedimentary rocks. You put in the yellow, please. Okay, so we know these words. You know that rocks can get weathered, right? What does that mean, weathering? When they get broken down, exactly. They get eroded, that means they get moved and transported, right? They move and get transported. They get deposited. Show me with your hands. They get deposited. And then they get lithified. They get hardened. Lithified means hardened. And they get compacted. But all rocks can become sedimentary rocks. This is how we're going to start using the chart now. Sedimentary rocks, if you weather them, can eventually get deposited and lithified and they can form sedimentary rocks again. Igneous rocks can get weathered, transported, deposited, lithified, and form sedimentary rocks. Metamorphic rocks can get weathered, transported, and lithified to form sedimentary rocks. So all 3 rocks can become sedimentary rocks. Do you understand that?
Yes.
Okay, good. Moving on. Oh, still going. So, this is a sedimentary, here's an igneous rock becoming a sedimentary rock. The igneous rock can break down, make clay and sand. Those sediments form rocks. Clay can become shale. Sand can become sandstone. Okay? So igneous rock can break down. You end up with shale and sandstone. A metamorphic rock like gneiss can break down. You end up with, you're not looking at your paper, we're looking up here. It can become, I told you I will tell you when you have to write. It's going to be yellow. Metamorphic rocks can become clay and sand. They can be transported. They can make sedimentary rocks. You can end up with shale and sandstone again.
That's nice.
Because those rocks break down. They have silicon in them and oxygen. They're silicate rocks. A sedimentary rock can become a sedimentary rock if it's weathered as well. Also, it can happen with chemicals, like when you have caves and stuff. We don't have to look at this right now. Now in Michigan, we're talking about the bedrock. Remember the parrot rock, the layer of soil way at the bottom. Most of Michigan's bedrock is sedimentary, and this is because of the glaciers. So what I want you to do is to go to your picture of Michigan. And right here, do you see this dark line on here? Trace over with your pencil. Keep that dark. Trace that line with your pencil. Okay. Just a minute, please. Okay, back to this. So you don't have this line on your map, but if you could just sort of sketch it in, this division line here somewhere, just sort of sketch it in with your pencil. You don't have to be perfect on that. It's halfway through the UP, the Upper Peninsula. But once you've done that, the eastern side of the Upper Peninsula and all of the Lower Peninsula is pretty much sedimentary rock when you get to the bedrock. This part here is igneous and metamorphic, and it's much older than this part. We'll find out later that these parts of Michigan were separated and they came together. So this is from a different rock formation than this is. So the sedimentary bedrock, I'd like you to color orange. And the igneous and metamorphic, I'd like you to color blue. Okay? So this part is going to be blue, and all of this is going to be orange right now on your map.
So all the rest is sedimentary.
Okay, now that your map is colored, and we know that this bedrock is sedimentary and this bedrock is igneous and metamorphic, we're going to talk about the sedimentary rocks that are found in Michigan. Now you will notice at the bottom of your page, underneath the map, there are a bunch of rocks. We're going to be labeling each of them as S for sedimentary, or I for igneous, or M for metamorphic, and you're going to find out what those are throughout the rest of the lecture. We're starting with the sedimentary rocks. When I show them to you, please write a capital S next to these rocks. Sandstone, shale, limestone, rock salt, and rock gypsum. Please write an S next to those rocks. All right, good. So, Michigan's got a great history. This is one of the reasons we've got a lot of sedimentary rock there. Michigan's been sculpted by 4 major glacial advances in the last 1.8 million years. So on your paper, you're going to find that on page 3. Wait, is that page 3? Yes. The first question on the top of page 4, they ask you the question, Michigan has been sculpted by how many major glacial advances in the last 1,800,000 years? How many? 4. 4 goes in that first box. So glaciers are why Michigan looks like it does, and that's why we have so many sedimentary rocks. They've been dumped here by glaciers. So as ice advances, remember we talked about this, it scours the ground, it digs it out. There's a lot of abrasion going on, and it digs stuff out and it moves material. So most of the rocks we have here from Canada and North America, it brought down. Then when it retreats and it leaves behind the water and whatnot, you have a different sort of topography. You have different landforms on top. New landforms. You have kettle lakes and you have mountains and moraines and all sorts of hummocks and all sorts of things. Now in Michigan, we live on top of complex group of sediments deposited by the glaciers. Look at these different colors. These are the different kinds of rocks. Isn't that crazy? It's just really nuts. This is a bedrock map. What will these sedimentary rocks become over time if they keep compacting and hardening? Sedimentary rocks, right. Sedimentary rocks. So now this is important. Here we have a picture. We have glacial deposits, and we know that they are younger than the bedrock on which they are resting. So let's look at question 2. Question 2 is, what's older? Michigan's glacial deposits or the bedrock on which they're resting? Which is older? The bedrock's older. The bedrock's older. Because the bedrock is down, then the glacial deposits come on top of that, and they are younger. Our sedimentary rocks, a lot of them came from oceanic and warm water environments, as you'll see. That's why we have so many fossils that are warm water fossils. The question on your test is going to be different than this, so make sure you read the question. So let's look at the Devonian age sedimentary rocks in Michigan. For one, we have the Petoskey stone. So your third question at the top of page 4, Michigan state fossil is a fossil coral that lived in the seas some 375 million years ago. Name it. What's it called? Petoskey stone. You don't have to know Hexagonorrhea percorinata. Petoskey stone. And it's a beautiful fossil. When we get to fossils next, I have lots of examples of Petoskey stones to show you. Michigan gets its sedimentary bedrock layers because the rocks were formed mainly in these warm water environments, which ended up making limestones. Some of these were the life forms that existed way back then, 375 million years ago. Very different from what we know today. Some are same, but some are very different. Look at this critter. In fact, this globe shows a picture of what some scientists believe, many scientists believe, it may have looked like during this Devonian time. 385 million years, 75 million years ago. Where do you think Michigan is going to be? Right there. Right here, Michigan right
It
there.
kind of looks like Benji.
Okay, moving on. Some of the Michigan Devonian rocks are on this chart. You don't have to know that. Now, let's go to igneous rocks. In the big giant banner on page 4, igneous rocks form from molten rock or magma in the subsurface or from lava. So all you write is molten rock, magma, or lava. All you write in there is molten rock, magma, or lava. So here we go with the chart again. Can all rocks become igneous?
No.
Yes or no?
Yes.
Yes, they can. If sedimentary rocks melt underground, deep inside the earth, they can become igneous. And then cool. So they have to melt and then cool, become igneous. If metamorphic rocks deep inside melt and then cool, they become igneous. If igneous rocks melt and then cool, they can become igneous. So all 3 rock types can eventually become igneous. Does it happen very, 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 very fast?
No.
It takes a while. So any existing rock, igneous, metamorphic, or sedimentary, can be subjected to enough heat or pressure causing it to melt. Molten rock is called magma. Hang on. And here we go. Fill out the rest of the box. Fill in the words, please, as you see them. So, as it says here, when magma cools, you write that, it becomes an igneous rock. Magma that comes out of the surface of the earth is called lava. You write that. And when lava cools, it becomes an igneous rock. We've had this already. It's nothing new, but it's just sort of bringing it back home again. And the kind of igneous rock form depends on what was melted and how it's cooled. You'll learn more about this in college. Igneous rocks are based on composition and texture. You'll learn more about that in college too. Now in Michigan, igneous rocks make up this western upper peninsula parts and metamorphic. We've already colored those out, right? Here are the igneous rocks. Go back to that page that has the list of rocks, and you're going to put a letter I next to each of these rocks. Put a capital I next to granite. Your rocks are in alphabetical order, so it's easy to find. Put a capital I next to basalt. You've seen that one. Put a capital I next to rhyolite. You've not seen that. It's similar to basalt if you look at it. Put a capital I next to granodiorite. When you get into college, and you will need to know these different forms of igneous rocks. They're not difficult to learn. And then pegmatite, it's got the big crystals. Those are all capital I igneous rocks that you can find in Michigan. That's what's special about this PowerPoint. These are Michigan rocks.
Okay, we can find.
I have tons of rocks.
We're moving on. Now, metamorphic rocks. This is the next block. Metamorphic rocks are formed when heat and or pressure cause any type of rock to change. Fill out the rest of that big giant space, please, on your last page. All right, so we know metamorphic rocks are formed by heat and pressure. And any rock can become metamorphic if it's subjected to enough heat or pressure. So can sedimentary rocks become metamorphic?
Yes.
Yes. Pressurize and heat them, they become metamorphic. Can metamorphic rocks get metamorphic again? Yes. Pressurize and heat them. Can igneous rocks get metamorphic again? Yes. Pressurize and heat. And before I continue the PowerPoint, notice that there are pictures at the bottom of your last page there. Those are pictures of the last glacial advance and what it looked like as it retreated and how it left Michigan looking like it does. That's just for your own benefit, okay? You can look at those when we're done. I want to finish the PowerPoint here. So a metamorphic rock can become metamorphic if it's igneous. Let's take basalt. Basalt can be changed to metabasalt. And how about sedimentary rocks? You can take limestone or dolomite and they can become marble. You know that. You know limestone can become marble. Now sandstone can become quartzite. We did not talk about this, but I actually have some quartzite here. So I have 3 beautiful pieces of quartzite on my table. Let me show you guys. I don't know if you can see it. Nope. There we go. See with the light. Beautiful quartzite. So sandstone can metamorphose into quartzite, okay? If you apply enough heat and pressure. That's not one that you need to know for your test. And we know that shale can become slate. All right? So sedimentary rocks can become metamorphic rocks. Can metamorphic rocks become metamorphic rocks?
Yes.
Sure. Slate can become phyllite. Phyllite can become schist. Schist can even become gneiss again. Kind of crazy. Talk about a cyclical, huh? Big cycle. And again, igneous and metamorphic rocks are up here in the western half of the Upper Peninsula. And here we go, the final thing. Go back to the list of rocks. And it should be all the ones that are left, but I'll call them out to you. The metamorphic rocks that can be found in Michigan, some of them are iron ore, schist, slate, quartzite, marble, and gneiss. Go ahead and label those with a capital M. All right, and 4 of your test rocks are actually schist, slate, marble, and gneiss, correct? So moving on. Oh, you don't know that yet. You haven't seen your test rock thing. That you're getting that today. And just more about Michigan. We have a state gemstone. Gemstone is called the Isle Royal greenstone. It's a metamorphic mineral. It's beautiful. So our state rock is Petoskey stone, right? Our state gemstone is Isle Royal greenstone. This is the important thing. Read this with me, please. The rock cycle does not go in just one direction. I'm going to start again. I've got to hear you speaking together. Try it again. The rock cycle does not go in just one direction. Any given rock can go through any part of the cycle any number of times. So, join me as you figure out what I'm saying here out loud. Sedimentary rocks can become sedimentary rocks. Metamorphic rocks can become sedimentary rocks. Igneous rocks can become sedimentary rocks. Now we're going to go here. Igneous rocks can become igneous rocks. Metamorphic rocks can become igneous rocks. Sedimentary rocks can become igneous rocks. Do metamorphic now. Metamorphic rocks can become metamorphic rocks. Sedimentary rocks can become metamorphic rocks. And igneous rocks can become metamorphic rocks. So if you pressurize and heat them, they're becoming. If you melt them, they're becoming. If you weather, deposit, transport, they become sedimentary. Do you understand the rock cycle even a little bit more now? Yes? And now you know about the Michigan rock cycle. Very good. Nice job.
Yay.